Good afternoon, everyone. My name is Vinay Kumar Mahato. I am doing my PhD in BHU under Dr. Ramit Singh. My topic is energy eigenvalue of a confined hydrogen atom using finite element method. Uh, this is the outline of my presentations. Uh, uh, Confined system gain much interest in recent years because these are the cases where the confined system can be studied atoms and molecules under high pressure and near surface donor state and impurity binding energy in quantum state. Uh, Finite element method is a numerical technique to solve a partial differential equation. Uh, Here we solve the Schrodinger equation that is also a second order partial differential equation. So in finite element method, we first discretize the domain into some finite element. Here, this is the domain. If we see for a radial term, this is at center 0, and if the confinement radius is capital R here, this this whole domain can be divided into some element, and and for each element we can approximate the wave function, because here in this curve the dotted line are the true solution, and if we approximate the solution using the uh, straight line, so here we take uh, approximation for each element. So for one element, let's say we take this element from R1 to R2, we can approximate the wave function as UR equal to N1R UR1 plus N2R U2, where uh, UR1 is the solution at point R1, and UR2 are the solution at point R2, and R is in between R1 and R2. And here N1 or N2 are the shape function, that is the interpolation function, which I take here linear. If I take this as a quadratic function, then the solution become more accurate, because here we take the straight line to approximate the true curve, but if I take quadratic uh, quadratic interpolation function, then the solution become more accurate. For simplicity, I take her as a linear. These are the properties of the shape function, that their sum must be 1, and at R1 N1 become 1, and at R2 N1 become 0. Similarly, at R1 N2 become 0, and at R2 N2 become 1. Here is the Schrodinger equation for confined hydrogen atom, where I took the calculation in atomic unit. So H cat become 1, uh, M become 1, and charge of electron E become 1. And first I need to convert this into a weak form. That means the second order term, I want to convert it into first order for calculation simplicity. For this, we multiply the Schrodinger equation into a test function VR both side, and integrate over the whole domain for 0 to R. And after integrating the first term by applying integration by parts, we got this term. And we take here that the uh, uh, test function is 0 at R1 and R2. So we get this term, and I study for two different potential. One is uh, impenetrable and one is penetrable. That means uh, the at boundary the wave function becomes zero for hard confinement, and at boundary wave function become non-zero for soft confinement. Now, if I want to convert this term into matrix form, so I approximate UR as N1 R U1 UR1 plus N2 R UR2, and here is DU DR. So UR1 is a constant because it is the value of U at point R1. Similarly, UR2 is also constant. So if I take derivative du dr, then it's become dn1 dr ur1 plus dn2 dr ur2. And if we convert this term into matrix, we got this multiplied by ur1 into ur1 ur2. And similarly for URVR, if we convert this term into matrix, we get this N1, N2 multiplied by UR1, UR2. And similarly, V effective is also that. And after calculating for each element, we sum up the whole domain, and we got the global uh, matrix K, which is the sum of K local and V local. And we got the global mass matrix, which is the sum of all elements of an M local matrix. And after solving this generalized eigenvalue problem, we got the eigenvalue which represents the energy of that system, and corresponding eigenvector gives the uh, wave function. These are my results, which is very similar with the previously published work. Here I use quadratic shape function. This is for impenetrable box, where wave function is zero at boundary. So at this is the confinement radius. So when it's extend to 30 atomic unit, this gives the an accurate energy eigenvalue of a free hydrogen atom in atomic unit. This is the wave function and the radial curve. Here we see that this is for confinement radius 2 atomic unit, where the wave function is 0 at a 2 atomic unit, and the B is for 16 atomic unit, where I make wave function 0 at 16 atomic unit. This is the result for penetrable spherical box. That means the potential is soft confined. Uh, For this, wave function is non-zero at boundary, so we need to extend the confinement radius much higher, so that we got the exact eigenvalue of a free hydrogen atom. That is in 30 atomic unit, we got minus 0.49. This is the wave function versus radius curve. So here we see that for here we set confinement radius to atomic unit. So it is soft confined, so the wave function is zero somewhere else, not at the boundary to atomic unit. And here I choose the confinement radius at r equal to solo atomic unit, where the wave function is non-zero at 16 atomic unit. Here is my conclusion that we see that the uh, if we increase the confined radius much higher, we get the eigenvalue of free hydrogen atom. And in plot 1 and 2, we show that the number of nodes are same for free hydrogen atom, but the wave function is squeezed inside the box. These are my references. I want to thank my supervisor and my senior for this help, and CSR for funding. Thank you.